Let's try to solve this problem here. A worker uses a pulley to raise a load of 120 kg through a height of 2.5 meter. So let's try to visualize the situation. You have a pulley. So assume the pulley is being hung at the ceiling, let's say. So let's say this is your pulley. Then on one end of the pulley, you have your load. And this load is 120 kg. Okay, let's write here 120 kg. Then it's being pulled by the worker. So you should expect on the other end, you should see a worker. Oops, the worker's hand should not be here. Should see the worker pulling on to the rope. Okay, and he applied a constant force of 1450 Newton, and this whole process of lifting up the load to a height of 2.5 meter takes 50 seconds. So let's bring that into our diagram. So we can see that this person is pulling the rope of the pulley. So you should draw the force probably around here. So this force is exerted by the worker onto the rope. So it's exerted by worker on rope, and the force is 1450 Newton. I know this is a pulley, so the tension will be transmitted over to the other side of the pulley. Thus, the load over here will also experience a tension exerted by the rope on the load here, and the tension should be 1450 Newton as well, because the tension across the whole rope here should be uniform. Okay, we assume this is a massless pulley as usual. Okay, so this object here will experience a change in height. So you can say that this object here experiences a displacement upwards by 2.5 meter, and you end up at a higher position somewhere around here. Okay, so this whole process here takes up how much time? 50 seconds. Okay, so I believe that's the situation. Everything has been labeled inside the diagram. The block doesn't necessarily have to start from the ground. You just have to start from a lower position and end up at a higher position. In this case, I'm drawing it hanging in the air because I'm saying that this is my ground. Okay, it doesn't matter whether the block starts from the ground or starts from somewhere, as long as it goes up by 2.5 meter. That's the main idea. Okay, so the question asks for what is a useful work done by the worker. So useful work done, it's a very interesting concept. It's like, okay, let's look at this situation here. The worker is trying to pull on the rope because the purpose of this work over here is to raise the load to a height of through a height of 2.5 meter. The purpose of this worker doing this work is to raise the load by 2.5 meter. So that's the main purpose. So when we talk about useful work done, right, we only talk about the thing that is relevant to the object being raised to a height of 2.5 meter. Okay, that's the main purpose of this motion over here. So there are two forces being exerted on this block over here. Let's use a free body diagram to show what are the two forces acting on the block over here. So if I use a dot to represent the block, you see that the forces that are acting on the load over here will be weight, because the object has mass 120 kg. Another one will be the tension. Okay, so these are the two forces that are being exerted on the object. So technically you can find the work done by the tension or the work done by the worker. They are the same thing. And you can also find the work done by the weight or the work done by gravity. So let's find both of them, then I'll tell you what is useful work done. Okay, so first one, we have work done by the worker. So work done by the worker, let's just call this F, okay? External force, right? So it will be the magnitude of the external force, magnitude of the displacement, and cosine the angle between the external force and the displacement. Again, when we are talking about this external force, right, we are actually talking about this tension over here. Okay, the external force indeed is pointing downwards, but the force is being transmitted over the rope, and technically what is exerted on the block is the tension. Okay, but the magnitude of the tension and the magnitude of the external force are the same. So let me write it down. So the tension should be equals to the external force in terms of magnitude, but the tension and the external force are in opposite direction. You can write it like this. Okay, so I can replace the tension. I can replace the tension here with the external force because they share the same magnitude. So I write here the magnitude of external force. I can just write magnitude of tension as well, no problem. Okay, then I can say the magnitude of tension is the same as magnitude of external force. Okay, both are fine. But here we are looking at the angle between the tension and the displacement. Okay, it's between the tension and the displacement. The tension is pointing upwards, and our displacement is pointing upwards as well. Okay, we are pulling upwards and the motion is indeed upwards, so these two forces share the same direction, so the angle between them should be 0 degree. Okay, should I just write theta first? Then let's substitute 0 degree. So if you substitute everything, 1450, 2.5 meter, 1, I believe you get the answer of 3625 joule. So this is the work done by the worker when this object 120 kg load has been raised by 2.5 kg. The worker does this much work on the load over here. Okay, next let's find what is the work done by gravity. Work done by gravity will be the magnitude of the weight, the magnitude of the displacement, and cosine the angle between the magnitude of the angle between the weight and the displacement. The weight is down here, the displacement is going upwards, so the weight and the displacement are in opposite direction. So you should expect the angle between them to be 180 degree. So let's do our substitution. Maybe 120 kg weight, mass, 9.81 acceleration due to gravity. The displacement is 2.5 meter, and cosine 180 degree is -1. So if you put all that in, you should get -2943 joule. So this is the work done by the gravitational force, or work done by weight. So I've calculated two things here, but which one is the useful work done? Okay, the first option is the work done by the worker. The second option here is the work done by gravity. So which one is the useful work done? The answer is none of them is actually the useful work done. Okay, so let me try to explain the concept to the best of my capability. So the work done by worker, as you can see, it's greater in terms of magnitude compared to the work done by gravity. What does it mean? It means the gravity is trying to pull the object downwards, but the worker is trying to pull the object upwards, but the worker is doing more work than the gravity. So it means by the worker is able to overcome the gravitational force to bring the objects upwards. Okay, the worker is overcoming the gravitational force because gravitational force is opposing the motion. The worker exerts a force to oppose the weight in order to pull the object upwards. Okay, so that's why the work done by worker is having a greater magnitude compared to the work done by gravity. Okay, next, useful work done is like this. If the worker choose to pull with a lesser force, technically the object will still rise as long as this work done by the worker here is equal or greater than the work done by gravity. If the worker choose to pull with a smaller force, technically the block will still rise upwards as long as the work done by the worker is equal or greater than the work done by gravity. If the work done by worker is equals to the work done by gravity, what happens is the total work done will be equals to 0. In that case, the object will not experience a change of kinetic energy, it will not experience a change of speed. So what will happen is the object will move upwards with a constant speed. Okay, but if our work done by worker is greater in magnitude compared to the work done by gravity, in like similar to this case over here, what happened is our total work done will be positive. Total work done is positive, means by the change in kinetic energy is positive. Change in kinetic energy is positive, means by the change in speed will be positive. So what does that mean is the object will be rising upwards while speeding up. Okay, but speeding up is not useful. Our purpose here is just to raise the object by 2.5 meter. It speeds up, it's just energy wasted in our purpose over here. Our purpose is just to bring it to a higher height. You can bring it up with a constant velocity, it's still fine, no problem. Okay, as long as it's able to rise up to the to rise up by 2.5 meter. So when we talk about useful work done, right, we are talking about the work done by the worker to overcome the gravitational force. So technically, right, the useful work done, right, the useful work done is just the negative of the work done by gravity, because we just need enough work to overcome the gravity. We don't need more work than the work done by gravity. Just need just nice enough to bring up the object with constant speed, then it's good enough already. So that is what we call a useful work done. Just enough work done to overcome the gravitational force to bring the object up by 2.5 meter. That's the idea of useful work done. So technically, useful work done is 2,943 joule. This is the answer. Okay, but you can also think of it that way. We think of it like this. The purpose of this process here is to rise up the object by 2.5 meter. So in that case, right, our main idea over here, our work done useful here, is to cause the object to experience a change in potential energy. Okay, because the useful work done here is to make the object rise by 2.5 meter. Or in other words, the useful work done here is to cause the load here to experience a change of gravitational potential energy. So you can do it this way as well, by taking UF minus UI. So this will be mgh final minus mgh initial. You factorize out the mg, then what's inside here will be the change of height. Your change of height is 2.5 meter. So if you do your substitution, you can write your mass to be 120. Your acceleration due to gravity is 9.81, and the change of height is 2.5, and you get the answer of 2943 joule. So this is also a method to determine the useful work done. Technically, the purpose is to rise up by 2.5 meter. So if you just check what is the change in the potential energy when this object rises by 2.5 meter, the amount of change of gravitational potential energy is equivalent to the useful work done. Okay, it's quite complicated to explain the word useful, but I hope you get the idea. Okay, next question 2. Question 2 asks for the input power by the worker. Okay, so this time is indeed we are specifically asking for the rate of work done by the worker. We know the worker does this much work during this amount of time. So what is the input power? What is the rate of work done by this worker over here? You just take the work done by the worker, divide by the amount of time it used to do this work. So the power of the worker is just the work done by the worker divided by the amount of time the worker used to do this work. So in this case, this is 3625 joule, then the amount of time elapsed is 50 seconds. So you can find your power of the worker to be 72.5 watts. So for every second that has passed, the worker is using 72.5 joule of energy to pull the object up by 2.5 meter. Every second, 72.5 joule of energy is spent by the worker to pull the object up with a force of 1450 Newton to pull the object up by 2.5 meter. So that's how we will solve the problem.